Good morning all and welcome to this Stratasys Redefine Possible webinar hosted by TCT. I am Laura Griffiths, Assistant Editor here at TCT Magazine. And for those of you who are unfamiliar with TCT, we are a platform of publications and digital products in Europe, North America and China, and also events in the UK, Germany, China and the US. For today's webinar, we are joined by Mr. John Jones, EMEA Materials Business Group Manager at Stratasys, who will be taking a look at what is possible with Stratasys 3D printing and digital materials. We are confident you'll leave this session having gained some valuable insight into possibilities for reality in advanced prototyping and production parts. Before I hand over to John, just a bit of housekeeping. There are 15 minutes at the end of this webinar reserved for Q&A, and using the chat facility, please send your questions directly and I can put them to John at the end of the session. You can do this throughout the entire webinar and we'll endeavour to get as many of your questions answered as possible. For any technical questions, please address those also to Kane Brennan, who will be able to help you. And with that, I'd like to hand over to John Jones.
Thank you very much, Laura, and good morning, everybody. Thank you very much for taking the time to join us today here on this webinar. Redefine Possible. This is the topic of the next 40 to 45 minutes webinar session, during which time I aim to try and bring you all up to date on the development of materials from the company Stratasys over the past 2 to 3 years specifically. But I will also take the opportunity, not knowing whether I have existing customers or potentially new customers in the audience, to very briefly update you on a little bit more of the background. I know many of our existing customers are very busy day in, day out working with the technology and their other commitments, so it's not easy to catch up on what developments have been going on. So I'm going to use this time also to bring you all up to the same point in terms of awareness of what materials have been produced and are available for the technology that you have invested in. Before I actually start discussing the actual material developments, I would like to share with you a few case studies. Okay, 3D printing is changing the game. This is not a theory. This is not a prophecy, but this is a fact of life. The world of 3D printing has changed dramatically over the last 2 to 3 years. But I'm sure many of you know it's been around for many more years than that. I think 25, nearly 30 years now. The original Stratasys systems were being released and customers beginning to benefit from them. But let me just share with you, first of all, 3 or 4 stories on how the technology is changing the way people do business. First of all, of course, the fundamental benefit of 3D printing is the freedom of design and geometric shape. Okay. We are no longer bound by the limitations of conventional manufacturing processes. In this particular case, the company Aurora developing a drone, jet-fueled propulsional plane, as you can see in the image here. And in this particular story, the benefit was manifold. First of all, purely by the fact of not having to create expensive tools for the various elements on the aircraft. The time to produce the first prototype model was reduced greatly by over half, and that's a statement by the company. So first of all, it's time to actually bring the first functional prototyping to market. That is a key advantage when using 3D printing. Okay. The other benefits clearly are this freedom of design. Okay. There are many limitations when using conventional processes. 3D printing allows the designers to ultimately design how they wish from the theoretical world into a real world, and this can make significant advantages in the design, in the weight ratio to the actual design of the part, which will affect, of course, greatly the fuel consumption and other very, very important statistics on this type of vehicle. Not only, of course, in the aircraft industry, but this can be applicable to any automotive or transport method. At the other end of the scale, we talk about direct digital manufacturing. In this particular case, the production of personalized parts. Not something that's new to the company Stratasys. We have for many years had a thriving industry with customers working in the dental and also the medical and hearing aid industries. Here is a case where the company Normal in the US has taken the hearing aid concept on a commercial level to the next point, where a customer can literally take a photograph or photographs of their actual ear using a coin for scale, send those photographs to the company normal, and they will produce a personalized earphone. As you can see, the blue shaped areas, these are formed specifically for the individual customer, so that the fit and the level of comfort will be enhanced greatly. Okay. Most importantly, this is not something that you have to wait for. The actual parts will be printed within hours of receiving the files, and the end customer is typically receiving their end product within 2 days. So personalization without the need for extreme time lag. All of this design freedom obviously is also allowing customers to enhance the performance in terms of weight ratio to power and performance of the parts. And in this particular story, what we see in that image there is a nozzle, a fume nozzle, devised by the customer Bell Helicopters. In this particular case, they decided not to produce the part, low volume part, for their devices with the typical tool, which would have cost over $120,000, but to actually print it. During the printing process, they took advantage of the 3D capabilities by reducing costs in the actual weight of the part. This was obviously an ability thanks to material and also design capabilities. So not only was there a cost saving thanks to the need not to have a tool, but the ultimate lower weight, 13% weight savings, was effective in actually reducing lower fuel consumption and ultimately resulting in lower CO2 emissions. So definitely 3D printing is also improving the environmental and sustainability of many companies using technology today. The final story, something that was also in the news a number of years ago, an interesting case where a UK Hawker Harrier jet, I think that is, had to make an emergency landing on an American aircraft carrier. As you can probably see from the image on the right, the front landing gear failed to open, so they had to use the table on the bottom right of the image to support the nose of the aircraft as it landed, which it did fairly successfully, but still there was some damage to that nose. Thanks to 3D printing, the US Air Force were able to print FDM material, some tools that would enable them to produce the metal parts, and also print a drill guide, which they did on mainland, but were able to send those parts out within a week and have that plane up in the air flying again in just over a week's period of time. And they claimed that if they would not have this capability, that plane would have been grounded for at least a month with normal processes. So another great story on how 3D printing is actually affecting the world around us today. So to summarize, 3D printing is basically actively changing the world around us in three key areas. The first being prototyping. This has been the bread and butter, particularly of the company Object as it was before the merger of Stratasys 3 years ago. And still this is very much the fundamental basis of the company's turnover where materials and hardware is concerned. But there are very, very interesting developments. In the area of tooling, many companies who've long had 3D printing technology in-house for the purpose of producing prototypes are gradually realizing that either the same technology or similar technologies that they've been using are also ideally suited to produce their production line setups with excellent and fast production line tooling parts. So very much an interesting area of growth. Very much linked to the prototyping, but obviously taking this to the next level into the production environment. And finally, and most, I think, tantalizingly, the dream of the DDM, the direct digital manufacturing process. Okay, the dream that one day spare parts, mass production, storage halls full of spare parts for the coming 10 years is a thing of the past. Printing parts on demand, putting short-run parts going into manufacturing is obviously an area where we as a company, Stratasys, are investing a lot of R&D money and time, both into the development of materials that will meet the needs in this particular sector, and of course also developing the machines, the systems that will provide the robustness, the repeatability, the consistency, and of course the speed that would be required in the manufacturing environment as we try to extend that short-run part production into maybe many tens, hundreds, or even thousands. So that's a quick overview and a glimpse of how we've been influencing the world around us today. I'm now going to, as I said, attempt to bring those of you who are not maybe completely familiar with the company Stratasys very quickly up to date on the fundamentals of the company. We are a dual technology company, as I mentioned briefly a few minutes ago. The company Objet, who is the Polyjet Israeli company, merged together with the original Stratasys company, which is based on the FDM thermoplastic technology. Okay, very, very simply put, these two technologies work in a very different way. The one, Polyjet, is jetting with a 2D printing type inkjet technology, a liquid polymer resin with a UV light, UV activator. As that material is jetted up to 7 million droplets per second, it is cured or hardened with a UV light source. And layer by layer, we create our part. On the other side, the FDM thermoplastic is a more conventional and probably more familiar with most of you process of taking a filament of real plastic, thermoplastics, driving it into a liquefier where the filament is liquefied and extruded, and then the process of creating layer by layer the parts is established. There's one very fundamental difference which will also become obvious as I explain in further slides, the differentiation between the two technologies and how they are used by our customers, and that is the layer thickness. I think that's the one major difference between the two processes just being explained in front of you now. On the Polyjet side, we talk about layer thicknesses as fine as 14, that's 14 microns, with a maximum thickness of 40 microns. On the FDM side, we talk about 10 times that. So the finest layer thicknesses are 120 microns up to about 350 microns, okay, at this moment in time. So this will, together with the material performances in the table I'm going to show you in a moment, ultimately show how the two technologies fit very snugly together, with the Polyjet being predominantly for the prototyping world, the FDM being mainly for the tools, tricks and fixtures and manufacturing of the future. Just to close on that, you see an image of all of the platforms we have on offer. The one image you don't see here, of course, is the MakerBot, which also belongs to the family of Stratasys portfolio, but I'm showing you at the moment what we call our professional range. There is a product as low as $10,000 and up to many hundreds of thousands of dollars to meet the needs and demands of each individual customer, depending on speed, availability and mixture of materials and build size. So now we're getting into the topic of materials in more detail. My favorite slide of all, this slide is basically a graph showing you along the horizontal line the impact strength of the material, ranging from 0 to 250 joules per meter. And in the vertical on the left, you see the thermal resistance, the HTT, in Celsius, along the top going from 0 to 250 degrees Celsius. Now what jumps out you hopefully immediately, and will also show how the coming together of the company Objet with Stratasys was an extremely good fit, is where we have the blue diamonds, which represent those materials which are defined as Polyjet, and the green diamonds, which are the materials that are available from the FDM product series. And as you can see, they fit up snugly. If you then add, as I just explained before, the benefit of the Polyjet material with its very fine layer thicknesses, being able to produce excellent prototypes with form, fit and assembly features with great surface finish and fine details, producing excellent prototyping. And then towards the further right and upper part of the graph, the green diamond showing where we have the performance materials, maybe not such a finer finish coming out of the printer, although there are post processes where you can also smooth, both chemical and mechanical. But you can see clearly here where the green diamond performance materials will offer the benefits needed in the more robust tooling and ultimately manufacturing environment. My favorite graph, as I said, if anyone ever asked me why or how the coming together of the two companies can be easily explained, I think this graph does it extremely well. So let's start by first looking more detail at the capabilities in the world of prototyping. The majority of the following slides will be related to the Polyjet technology, as I previously mentioned. It doesn't actually mean that STM is not a candidate for prototyping. It is used also in that area, but I think it's dominant where Stratasys is concerned with the PolyJet technology itself. Quick look back at the balance here, and I think it's important to show how much has happened in the last, 10 to 12 years. And with assurance, I can tell you that this continuing development and capabilities will only be advanced in the coming years. Okay, so this is sort of a taste of what's been happening, and hopefully to show the commitment Stratasys has here, and how we will, I'm sure, be providing our customers in the coming years even better technology materials to meet demands that will enhance the technologies used within each and every customer. Just quick look back, and said back down 2004, we began by introducing, this is opposite side, an Eden platform, fundamentally jetting a liquid polymer resin. The limitation here is that we could only print with one material at a time. Okay, it may be a rigid material, it may be a rubber-like or transparent, but there was only the capability to produce a single material here. So we were comparable to many other technologies in the market. In 2007, this is when we think we made the breakthrough. This is when we started to introduce to the industry the capability of simultaneously producing parts out of two base materials. Two materials with fundamentally different capabilities. The simplest example obviously can be printing a part with rigid and also rubber-like properties. Okay, that was a rigid part with possibly a flexible element, which possibly would have been done in a conventional process through a complex and very challenging secondary process. With the Connect system, you were able to produce those challenging parts in one pass. 2014, this is only 2 years ago now, we took the next step. We introduced a similar type technology, still using the same basic principle heads, but now able to produce simultaneously 3 different materials at one time. Okay. Obviously, this made the possibility of the complexity and of the capacity of the capabilities of the end parts even greater than previous. Okay, we could take, for example, our higher performance digital ABS material and combine also now with a rubber-like material while printing simultaneously. All right, so this was very, very important. And this was the moment in time where we started to introduce a form of color. The Connect 3 was the first of the object systems, or the Stratasys systems as it was already, that had a color material capability. We introduced a basic cyan, magenta, and yellow material. So not the full color gamut. We did only limit it to a 48 color gamut potential. So it wasn't producing full color parts, but it was enabling customers to highlight areas in prototypes that needed specific attention, possibly to highlight certain iterations where parts were changing in the first, second, to third versions, and possibly in some cases having color reproduction that was, if not exactly the same, but similar to the ultimate end part. Finally, we come to the most recent announcement in the world of PolyJet. That was back beginning of this year, 2016, where we introduced the J750. And this is the first time where we can start to talk about a true color reproduction. Okay, this system basically has the capability, to print simultaneously with up to 6 different materials. Okay, we enhanced the color offering. We maintained the CMYK offering, plus the ability to have rubber simulation materials or transparent or additional whites, grays, and blacks. Okay, so this was a first step into what we would call true color. Customers with this technology can have a choice of up to 330,000 colors in one particular part, which is obviously interesting. It's not unique. There have been other technologies in the past with similar capabilities, but what makes the system unique is that color availability is there, plus the ability to print with rigid, rubber, transparent, biocompatible, and other beneficial materials in the one system. Okay, the color stands out. It's obviously a very marketing interesting part. For me, I think this is also a very, very important breakthrough, because it will enable customers to have continuously up to 6 different material types online without having to do a material change. For those of you who have other 3D printing technologies or earlier PolyJet systems, you know, there is a period of time when you need to stop the machine, to change cartridges or canisters if you wish to change from one material type to another. On the Connect 1, 2, 3, there was to a degree of redundancy here, because we have 3 materials, but with the J750, there is a maximum of 6 materials continuously online. That means, for example, you could have our digital ABS, high performance material, the Vero Clear, transparent material, one rubber-like material, and 2 other additional materials that your business may be currently using. So the time needed to change materials, the downtime of the system, and also the waste of the material. We have to admit that there is also a certain amount of waste when exchanging material type to type 1 to 2. This has also been greatly reduced. And I think with 6 materials online, it will probably meet the majority of customers' needs, i.e. very, very little material waste due to material exchange as a result. So that's an update on the PolyJet technology. You now have an insight into where we're going. And as I said before, this is a continuation. This is where money is being invested in day and out, and we will see, I'm sure, in the future, the near future, further developments enhanced where possible based on the technologies already resulted. But if it's groundbreaking technology, obviously, for further machines that our customers will benefit from. Ultimately, just to put another point on the J750, the challenge to print a perfect prototype, something that will be coming out of the printer and looking and feeling like performing as the end part will do, is now something that is in reach. Okay, from the most complex of CT scanned images converted to a VRML file, as you see on the left, with brilliant color contrast and transparency abilities, to great reproduction of shoes with rubber soles and flexibility in the build, as well as true color representation. In the automotive industry, the J750 is wonderful producing varnishes for reproducing surface structures and textures to the finest detail that would normally be challenging and difficult lamination processes on regular prototype printed parts in the world. This is printed in one go, coming out of the printer with a minimal of cleaning required. I'll go on to that topic in a moment, or end parts that are simply going to look like the end product long before a final production run of that product is ever being considered. Right, another quick reminder here on the PolyJet materials. Again, bear with me if you are familiar with this. I'm trying to bring everyone up to speed. There are a range of base materials available with the PolyJet system. There are actually, I think it's 35 base materials available this day. They range from what we define as our rigid products. These are a range of materials with limited material characteristics, i.e. the performance material is not particularly good. It's there to look good, but the functionality is not to be compared to real ABS materials, but it will make for an extremely effective, because of the fine surface and surface detail, prototype. We have this material in a transparent material. We have it in simulated polypropylene materials, the Duros White and most recently Rigor, which I'll talk about a little bit later on. We have our Vero family. This is the fundamental base material, Vero, which comes in 4 different versions, changed only by color: Vero White, Blue, Gray, and the Black Plus. And also, more recently, we've taken the Vero setup and added pigments so that we also have the yellow, cyan, and magenta colors for the Connex 3 and J750 range. We've also then got a range of simulated materials which we define as flexible. These are the rubber simulations we call Tango. And the Tango materials differ by shore hardness. There are shore hard 27, 30, and 65 as the base material, the raw material coming out of the system, which comes with a black, gray, white, or transparent appearance. Sorry, black, gray, or transparent appearance. We also have a version of the Vero material which has a greater degree of process, which we define as medical. Now, these materials are defined as medical because they come with biocompatible certifications, of which you can find a lot more information on our website. And this material has been used in the industry for boring guides in the dental market, for the production of hearing aids for many, many years, and also most recently a series of materials, Vero Glaze, Vero Dent, and Vero Dent Plus, specifically designed to look like perform for the dental market. At the high end of the PolyJet material portfolio, we have what we define now as our engineering plastic simulation. Again, we're talking about simulations here. We named the high temp material, RGD 525. I will be honest here and say that the definition high temp is reflected compared to the previous Vero materials, which has a HET of around about 49 degrees. Here, our high temp material out of the printer will have a HET of around about 65 degrees Celsius. For those needing a slightly higher thermal resistance, the material can be tempered in a programmable oven, and that can be pushed up to about 75 degrees. That's a single material usable on many of our PolyJet systems. And the non-plus ultra in the range of PolyJet at this moment in time is what we call our digital ABS, which has a thermal resistance of around about 95 to 100 degrees Celsius, depending on geometry, and a azimuth impact of around about 75 joules per meter. So those of you who saw the graph earlier on, you will have seen that this is the high-end material on the PolyJet range, but only available on the 2K and above systems. It is a two-component material, therefore we require a CONIX or higher grade system to enable you to use this material. Okay, as I said, it's actually 25 base materials, but thanks to the potential of making digital materials out of these components, we have a claim of being able to replicate around about 1,500 different material characteristics. Okay, let me explain that statement in a little bit more detail. A digital material basically is a composition of two base materials. Okay, the primary, which could be a rigid or flexible material, printed simultaneously together with the secondary material, which again could be a rigid or flexible, depending on the required outcome of the end part. Those two materials will be kept in separate canisters in a liquid form, jetted simultaneously, as on a 2D printer, and at the point of curing, i.e. on the layering and the bed of the printer, they will cure, harden, and form a new third material, which we will define as a digital material. Okay, one of the areas in which Stratasys has pioneered 3D printing it was in this conjunction of printing simultaneously rubber and rigid materials. So using a Vero or even a digital ABS material together with a combination of rubber material allows you to produce a greater range of Shore A values. So I mentioned before the Tango Black Plus, for example, has in its pure form a Shore A value of 27, okay, which may or may not be suitable. But when you print it in a digital mode and add a component of rigid material, which you can do in various stages, you can have incremental Shore values going up to 95. So a part, whether it be a cable, a flex cable and a plug, earphones, a toy, a dress even, or a box or a surface structure can have its rigid components with its soft touch, its flexibility, with its haptic end effects printed in the one process. So a very, very extremely flexible and unique process as it was back in 2007. There are attempts to simulate this from other technologies during the last few years, but we still remain a clear leader in the development of this type of prototyping. Another development here, and this is something you'll see with Stratasys when we do introduce a new material, where benefits are available on the PolyJet side to interact with existing materials, we will of course enable as quickly as possible that new digital material. In this particular case, what we've taken is Tango Plus, that is a translucent rubber-like simulating material, and then we will print it simultaneously on the CONIX 3 with two other rigid materials. In this particular graphical case, taking the cyan and the yellow materials, you can have a gamut of color ranging from transparent on the right to opaque color on the left, with a degree of Shore A values. Okay, so obviously on the right-hand side, where it's complete transparency is available, you have the Shore A 27, and as you move from the left to right with increasing amounts of rigid yellow and cyan, you will have a greater Shore value to 35 or in fact 95. Darker is hard. Obviously, the more the opaque component in the actual part, the more rigid the part becomes. So there is a limitation in terms of transparency, opaqueness, and the amount of flexibility, but still, for some customers, an interesting opportunity given by the CONIX 3 and above technology. So let's start looking at some of the developments over the last years. New advanced materials for functional prototyping. All right, now on the screen you can see here a number of application areas where we have made some breakthrough. Fundamentally, the digital ABS is the key development here. This is what's taken us from the prototyping realms into the realms of tooling, producing even injection mold forms with the digital ABS. Materials such as the strength of that material, particularly where as an injection molding form there is a bolt in the actual mold itself, and possibly also as important the actual presence of temperatures of up to 220 degrees Celsius and beyond are only present for a short period of time. This enables the digital ABS material, even though its HDD is only 95 to 100 degrees Celsius, to still be used in an environment where temperatures are up above 200 degrees for a short period of time. Again, geometry dependent. Other materials developments, improvements to our Tango world, so the development of the rubber simulation with greater tear resistance, that's something that's been going on, and also the introduction of what we call the Vero Clear material, which was a true transparent material, printed and polished. It can achieve results measurably similar to plexiglass in actual fact. Now let's just concentrate a little bit more on the digital ABS material, as it is the key material in the world of PolyJet. Just a reminder, we have here a 2K technology. Okay, we have two elements. The RGD535 is the element which provides the HTT, the high thermal resistance, and together with that we add the 515, which is the material with the higher toughness. Okay, these two elements, by the way, will not be effective, will not work on their own, such as the downside on each. So one has the higher toughness on its own, it would have extremely low thermal resistance. The higher temperature material would have an extremely fragile element to it. So together they are strong, alone they will be weak, and therefore they are only available as a 2K component. The original ABS came with a green color to distinguish itself from other materials, and a few years later we introduced the ivory version. So take away the 535, add the 531 component, and you have an ivory version of the same digital ABS, exactly the same data sheet, simply a different appearance, which was desirable for some industries and applications. So one important step that has happened during the last year or so was the introduction to our systems being able to use the VRML file format. Traditionally, we've taken an STL file from the CAD system, and then it was the job of the user interface to the printer to define by shell which property, i.e. if you were using dual materials, rigid and soft, that was a manual process of identifying which part of the actual product or part was going to have a flexible element or a rigid element. As we introduced the color, the 3K color on the Connex 3, you could then have, as I said, a gamut of up to, I think it was 45 different shades of color. This wasn't extended simply because we didn't believe the task of manually trying to create something as complex even as the image on the top right of the screen. Here they have fundamentally 92 shells, each of those shells basically being a different color zone. Okay, in the previous process, that would have meant an operator having to click manually per shell and select from a drop-down menu in the user interface the required color. Today, we can talk about the import of a VRML file, which will make this job far easier and actually allows them the true color expansion in the business as we see it with the J750. Okay, so just a quick overview here. So what would happen is in the CAD world, the designer will design the parts, will select the palette for colors for features even in the future. They will then assign the colors via either an object swatch, which is available for the Rhino and SolidWorks CAD systems, or through an RGB automated process. That format of VRML will then be exported through the interface to the Object Studio, where once importing the VRML, the system will do a cross-check to make sure we have now the correct materials in the system. So if there was color required, the system would obviously make you aware of the requirement of the CMY white and possibly black material cartridges in the system. The only thing the operator then need to do is position the part onto the build tray. There's multiple parts, obviously, there may be some need to manually optimize and begin to print. Okay, it has never been easier to get fine detail and color from a 3D printer as it is now with this new process made available in the Connex 3 systems available in the market today. Okay, staying on the topic of polyjet, more recent introduction was a simulated polypropylene material. Okay, when we introduced this originally, you may forgive me, forgive me if this is something you will record. It was initially called Endure. We had a legal challenge there, unfortunately, so we had to change the name. The product is now called Rigor, RDD 450, and this is the material that we would recommend when you are trying to produce prototypes that should simulate a polypropylene part. Okay, it comes in a white color. It has enhanced toughness, and when we talk about enhanced here, we're comparing again to the base Vero material. Okay, so the toughness of 30 to 35 joules per meter, elongation break 20 to 35, and a temperature resistance of around about 54 degrees Celsius. Now, again, if you compare this to the real plastics in the real world, this is nothing spectacular. However, it is in all aspects an improvement by a considerable amount to the base family of Vero materials. Okay, so there is a clear benefit for many customers who are producing basic prototypes that do require some form of post-treatment where thermal resistance is an issue. Maybe for the 49 degrees is sort of a just on the line of acceptance, whereas here the 54 degrees will provide a little bit more stability. And obviously the toughness and the lid mesh and break gives the parts also greater flexibility. So if the part is not a static part, if there is some flexibility needed, if there are living hinges and clips in the process where possibly the Vero family would have failed, the Rigor material is going to be a very, very good alternative solution. Of course, it has the same dimensional stability and great surface quality of all the materials. And what's key here is, you forgive me for talking about multiple material developments, the 2K and the 3K developments, driving obviously an interest towards the multi-K systems. But in this particular case, Stratasys has remembered its very loyal install base of Object 30 customers, the Eden family, systems where there's only a 1K material capability. So this is a single material that will be supported on all of the install base, both single and 2K and even 3K systems. Okay, so I think it's quite an important point to note. We've not just moved on. We do try, where possible, to enhance the material capabilities and allow our existing install base to benefit from developments when possible. Another little graph, a little favorite of mine. You'll see again here, similar along the horizontal, it's showing toughness on the thermal, the thermal on the vertical. Just to give you an idea of where the Rigor is sitting in, you can see on the left-hand side of the screen, we have the Vero with toughness in joules per meter around about the 20 mark, and the thermal resistance just below 50. The alternative prior to the Rigor being introduced was Durus. Okay, that was the polypropylene simulated material that we had on offer, and we still have on offer at the moment in time. That was a material with a far greater toughness than the Vero family. As you can see, it's around about the 40 to 50 joules per meter, so it was excellent for the production of clips and living hinges and the likes. However, through the inherent problem that we have, the challenge of the polymers used, this meant that the thermal resistance was very low. Okay, so just above the 30 degrees Celsius, which meant this part was very, very prone for warping, even in an environment on a hot summer's day in the UK. And it's feasible that this part could have been due to some warping through extreme temperature, i.e. above 35 degrees Celsius. So it was a challenge, and this is why I think the Rigor material is so being welcomed, in that it provides a greater thermal resistance, a far greater thermal resistance than the Durus, slightly better than the Vero, at the same time a toughness that is fair better than Vero. Not quite as good as Durus, but good enough for many application needs that our customers have in the field today. Finally, the graph just shows you, to put it all in perspective, how much better the digital ABS is. The investment in the 2K technology does provide you with a far superior material. Again, that's thanks to the ability of the technology to take two base materials, combine them, and have the benefits of both, with joules per meter toughness of around about 75 and a thermal resistance of 90 degrees after tempering with that ABS material. So, one of my favorite topics, having been around with Object for 7 years, this was always, as far as I was concerned, the holy grail. challenge that the company's worked on for many years, and since 2015 was able to provide a solution initially for the Connex 3 range, but I can assure you we will be gradually releasing this soluble support material for a wider range of products from the coming years. Okay, we did actually introduce for one specific product a soluble solution a year earlier, but that was a dedicated solution for a dedicated platform. This is a generic system that will be released on multiple platforms, and also has a very, very important capability of a hybrid solution. Okay, for those of you say familiar with other soluble support solutions, I'm sure you know that they are dedicated. So the part is printed in the system, it's taken out of the system, and it must then be placed into the jacuzzi, the bath, the process, which can take a number of hours to complete depending on the complexity of the parts. With the soluble support 706, as I'm talking about now, we call this a hybrid solution. Okay, so the hybrid solution means that there is a fully hands-free process. You can take the part out of the printer and place it into a number of baths or jacuzzi where there will be a chemical, mechanical process of removing the support structure. And again, depending on the complexity of the part and the amount of support in place, anywhere between 2 to 24 hours for the majority of parts can be cleaned, and a simple rinse off at the end of that process. But there's also a semi-manual process in which you can remove bulky areas of support structure before placing into the hands-free process. So in this way you can reduce in some geometries the actual process of removing that support structure by time, to a greater or lower degree, depending again on the geometries. Or, and this is the key here, and this is why for many years, we claimed the original support structure, the 705, was still, for the majority of prototypes, the best solution, because it was the fastest way. By placing the part into a water jet and removing the support structure by hand, you can have the part ready to be processed, to be looked at, to whatever's needed to do with it, with only a few moments. Okay, in minutes you could actually do this, again depending on geometry and complexity. So that was always the big advantage. It's great to have soluble solution if you need or you're willing to accept a 12-hour waiting time printing or cleaning overnight. That's obviously a great solution, but for those of you who would like to have the prototype after printing is completed in their hands at the shortest possible time, the water jet process is always going to be the winner. And I'm happy to say with the new soluble support 706, you have the choice. You can make the decision at the moment that the part is printed and finished to put it into the hands-free process, to semi-remove some of the support structure if the geometry allows, and then put it into the hands-free process, or to take it directly into the water jet and remove as fast as possible. Okay, so that concludes the overview on PolyJet. I'm now going to move on to FDM materials. Quick overview. Here we also have a range of materials. The standard, where we have the ABS materials. What we define as engineering plastics, where we have the polycarbs and the most recently introduced nylon 12. And the high performance materials, where we have the Ultim and PPSF materials, which I'll talk about in a few moments. There's also a specialty products, which I'll touch on briefly, soluble cores, soluble support, and also volume packaging, which was also introduced to the FDM world recently. Quickly looking at the first new material introduced in the recent years, and that was FDM ASA. Okay, basically ASA is defined as taking ABS to the next level. The first and most, say, beneficial benefit of ASA compared to ABS is it is far UV stable. Okay, so we have some data on that in a moment, but this is the material where the part is going to be subject to continuous UV light, where the degradation of the part or the color of the part is something that's not desirable. The ASA is going to provide excellent results compared to ABS materials. It will also have enhanced mechanical properties, so you're not going to have to accept poor datasheet properties just to get the UV stability. The ASA is in all accounts better actually than the regular ABS material as well, so a plus there. It will be coming, or it does come in available up to 8 different colors, so you don't just have the black and white here. You can also, if you need to have end color parts, again for definition or for even marketing purposes, you can print in a range of standardly available color parts. and as I said before, it is actually stronger and tougher than the ABS M30 material. So you have these additional abilities plus a stronger and tougher material compared to the ABS M30. Good news is it's available on basically all of the Fortis range, 360, 380, 400, 450, 900, and also has layer thicknesses from 120 to 330 microns. One of the nice features here of the strength of this material compared to the ABS is basically its ability to have a weaker, less used material for what we call the sparse mode print. So if you had a volume part, if you had a solid part, and we're using a dumbbell here for effect, you can see on the left the sparse build mode, which is there to lower the light of the print job. It's also reducing the amount of material and print time. You can see here the finer honeycomb structure. This dumbbell, printed as effectively as it could be in ABS mode, would be a weight of 1.11 kilograms. On the right-hand side, you see the same parts printed in sparse mode, but with a finer sparse mode. You can see clearly the honeycombing is far more sparse, i.e. there is less material used. That means that the print time is shorter, and also the weight, the overall weight of the part is considerably lighter, nearly half the weight, a saving of 63% here. So one of the benefits for a part that is going to be used in some form of production or tool, jigs and fixtures is a very interesting aspect of the ASA compared to ABS material. I mentioned there's some data to point on the comments here. Color resistance fading, so based on the delta E factor here, the table on the left, you can see that there is a fading of delta E for the ABS M30 over a period of 1,000 hours of 26. Okay, delta E with the ASC over 2,500 hours subdued sunlight, the failure is only 0.8. And we're stating here that actually a differentiation between less than 1 delta E is even not noticeable, so you can see clearly here a great improvement. There is also some drop-off in material properties over a period of time. You can see on the graph on the right in black, the actual ABS M30 does drop off quite considerably in terms of its performance, here shown as elongation of break. Out of the system with 9% elongation of break. After only 500 hours, that part elongation break drops to 1% and it remains entirely stable to 1,000 hours. In the greenish color, representing ASA, coming out of the system at around about 10% elongation of break, and that's maintained. After 500 hours, only dropped by 1%, and even after 1,000 hours, we still have a 7% elongation of break. So two areas where the durability of ASA compared to ABS is also performance enhancement compared to the ABS material. A quick table with more data. Fundamentally, what we're telling you here is that in every aspect on the data sheet, the ASA is improvement. Okay, there are therefore no real disadvantages moving to the AS material. Pricing-wise, it's similar. So there is a great opportunity here. And for those of you who are using ABS material with the SDM technology today, we would strongly advise you to consider the SAA. You can contact us any time to find out more about how you could get a sample or possibly do some testing on your own and benefit from this great development. Okay, another development in the world of FDM was the introduction of nylon 12 back in 2013. Okay, this was basically a breakthrough in terms of the flexibility or elongation break of an FDM part. Up until this moment in time, we were only talking about flexibility in the realms of a few percent. So now with this 30% elongation of break factor, we can talk about SDM printed parts with a degree of flexibility. Production of clip functions, living hinges is now something that can be considered. In addition to that, what is very important about this material is that its Z strength is greatly enhanced compared to other materials. One of the challenges in the SDM world is to get the data point in the Z-axis as close as possible to the data point on the X and the Y, okay? The FDM parts are never isotropic. The data is never the same in the X and Y direction. Typically, other FDM materials from Stratasys will be around about the 70%, 75% mark. But with this purpose-developed material from the ground up, our engineers have been able to establish a Z strength comparable to X and Y of 90%. And that's something where we are investing a lot of time and money in future to make sure that this theoretical weakness in an FDM technology is being reduced as much as possible. Okay, it's available currently only in the black. It has, very importantly, also a soluble support that's coming along. So many of the materials are compatible with a breakable solution where the support structure is manually removed. But we also have a number of materials in the FDM world with soluble support. I'm happy to say the nylon 12 comes also with the SR110 soluble support structure. Okay, and it's also got the highest impact resistance of all the FDM systems with a 200 joules per meter impact. And it's also supported with all 3 slice thicknesses, so there is no loss of layer thickness with this particular material from the systems you're using. Obviously, benefits here. Clearly, the automotive industry was quick to pick up on this. The development and production of tools, jigs, and fixtures for this particular segment has shown clear advantages through the performance of the nylon 12 material. Producing lighter and stronger parts, again, ability to print in 3D a part will enable you to optimize that part's design and structure. The speed to be able to produce these tools thanks to 3D is a great advantage for production line assembly, and again, the performance and capabilities of nylon 12 support the needs of many of those requirements. Fine, another very, very interesting issue here. It's not directly related to the material development, but also very, very important when we look towards manufacturing, of course, is the speed of the printing process. In 2016, we are introducing a high-speed FDM solution, which we believe will be very interesting, where parts are not that demanding where the surface structure is concerned. So ultimately, this is an acceleration kit. We're introducing the T40 tips, which, as I'm sure you can guess, are basically enabling the system to print with thicker layer thicknesses. Okay, so we're basically putting more material down per layer. This is obviously going to increase the speed in which it takes, the time it takes to print a part. The downside is the thicker layer thickness. As I said, they would not be suitable for every type of application, but where the surface structure is not key, but the reliability, the accuracy, and the strength of material is key. We believe this is an excellent way forward to further increase the optimum use of the systems available today. One other development that we've acted onto, as I mentioned briefly, we've developed soluble solutions support structures for our base materials in the FDM world for many years, and some of our customers were using one of those soluble support structures as a sacrificial tool, or a soluble core as it was called then. We've now taken the principle here, the application, and we developed a specific soluble material with enhanced characteristics to meet this application need better than it has been able to do with the standard soluble solution. So the FT30 is now defined as an application material for the sacrificial tool material. It has improved performance, particularly where moderate curing temperatures are required, depending on the end process. And I said it's tuned specifically for this application. This isn't a tweaking or a misuse of a soluble solution material, but this is a dedicated material made for the sacrificial tooling application. So, final section in this particular part of this webinar is the development for the manufacturing world. Okay, I mentioned in the slide previously, the Ultim is our ultimate high-end performance material in the world of FDM. It is the parts where already customers have been benefiting, producing parts that are standing up to the toughest of tests, and in some cases even going into end part production where short series part requirements are needed, even in the aerospace industry. Just to give you a quick reminder, similar graph, different dots here, no diamonds and squares, but circles. But I think you see the same logistics here, where you can see clearly the Ultim 9085, both in impact and in thermal resistance, is a star, only bettered by the PPSF and the Ultim 1010 materials, but clearly a high performance material with great opportunities in the industry today. Recalling back to one of those first stories, that drone that was being manufactured in a unique way compared to conventional processes, it was the Ultim 9085 material, excuse me, that was providing the material capabilities, the low weight structural strength that was required for such a device. So this is where but the Ultim material is providing some of its most unique capabilities. Okay, moving quickly on, because the 980 has been around for a while. The introduction to 1010 Ultim took us to the next level, and it's definitely proving a very, very successful introduction, available on the Fortis 900, 450, and 400 platforms at this moment in time. It is an all-round top performer. It has the highest temperature resistance of all of the FDM materials, around about 213 degrees Celsius. The best fire-resistant material with the lowest coefficient of thermal expansion. It has the best chemical resistance. Now that's a huge how long is a ball of string statement, but fundamentally there'll be individual tests required, possibly from customer to customer. But if chemical resistant parts are something you're looking for, the likelihood that the Ultim 1010 is going to meet those needs compared to any other FDM material is strong. This material comes with a number of certifications. It has biocompatibility certifications. It can be used to produce parts in food processing where food contact is a challenge, and it has FST certification as well. So there are a number of standard certifications that come with this material with the packaging as standard. Okay. It has ease of use, and we're saying ease of use here. Unfortunately, there is no soluble support for the Ultim 1010 or the 9085. We still have challenges here due to the build temperature in the device. To have a support structure that is also soluble is still eluded us. But what we say here with the ease of use is compared directly to the other high performance material, PPSF, which is similar on the data sheet. It's not quite as good as the Ultim 1010, but the support structure for this material is extremely difficult to break away. The comparable Ultim 1010 support material is far easier. So we would expect any customer who has the need of PPSF material would immediately see the benefits of moving to the Ultim 1010, both from a performance and an ease of use in terms of removing that support structure. And it is the highest in terms of tensile strength FDM material in the market today. This is a little sample here of how it's being used. Basically, a few nozzle here in aerospace industries. And I think this is what we're trying to get is the message. This material with its certifications is really at the high end of the market scale and already has aerospace certification. Now, there are actual parts flying above our heads today in planes that have been printed on Fortis systems using the Ultim 9085 materials, and the Ultim 1010 has similar or better characteristics. So clearly, if it's able to meet requirements of such an industry, I'm sure there are many other industries that will benefit from this development. Data sheet points here. I think there's an overview. Basically, what we're saying, the Ultim 1010 outperforms the Ultim 9085 or PPSF in almost every aspect, in many areas greatly. There's possibly one area where if you are an Ultim 9085 user, i.e. you do have the Fortis and this is the material of your choice and you're sort of getting your ears pricked by my information here on the 1010, please be aware that there is one area of deficit, and that is the eyes of impact, the notched, the rigidness, the brittleness of the system material here. This is a deficit here. So this is possibly the one area where you may consider to stay with the Ultim 9085 compared to the 1010. In all other areas, there is an enhancement or a benefit by moving from the 9085 to the 1010 as a base material. Just mentioned before, aerospace implementation is possible. There are two versions of the 1010. Should you start to become interested in this material, if you have the systems availability, please note that there is a CG version, a certified grade. Basically, it's the same material technically, but we obviously have the capability of providing all the necessary information on the raw materials and tracking the production that's required in certain industries. So the 1010 CG certified grade material would be the material of choice. If you're an approved airspace, Airbus, for example, supplier, that would be the material that you would require in order to meet the stringent requirements for such an industry's application need. So finally, to close this session, I'm talking about something that's related to materials, but not directly materials themselves. We are obviously always looking at ways to enhance the performance of the overall system. Traditionally, the STM canisters come in a 92 cubic inch system. and we introduced some time ago now the 184. You can guess this has the double of the capacity, which enables systems to be unattended, i.e. building over the weekend for over 90 hours. Okay, so there's no need with these larger volume canisters to have someone pop in over the weekend and replace a canister that may be extinguished. Okay, this is a standard option. There's no special upgrades, material options needed. There's even also a volume discount passed on in this larger volume canister. So because of the volume in the canister, we're actually seeing a direct comparison to the regular pricing materials of about 5% on those materials that are available here. Okay, basically at this moment in time, it's available for the ABS M30 in ivory and black with its soluble support, and also the polycarb and its support structure. Obviously, if there's a demand for other materials, we take that on board and possibly can introduce other materials for this volume canister in the future. Finally, taking that volume concept and the unattended operation even further, there's the Extend 500 Filters Plus canisters. Here we have 5 times the volume of the regular canister, so obviously up to 200 hours of unattended run per box. Similar cost saving compared to the original canister volume of 5%. Here there may be possible upgrades needed. The canister is so large it actually stands outside the system, so there will be some modifications needed on existing platforms, and will support again the ABS M30 ivory and black plus support, as well as the polycarbon support structure, as well as the Ultim 985 natural and support structure for the future. That completes my part of the webinar. I thank you all very much for your attendance and your attention, and I believe we're now going to open up the session to any questions that you may have been submitting during the period.
Yeah, thanks for that, John. Yeah, we are moving to the Q&A section right now. We've already had some great questions come through, but do continue to send those in as we go on. If we don't actually manage to get through your question, the team will follow up with you individually after the session. So we'll kick off with one now. So one person wants to know, when will the soluble support be available for legacy products?
Okay, so the 706 material that's referring to, so at this moment in time, is available on the Connex 3 500 formats, and will be also introduced onto the Connex 3 platforms with a smaller build size, so the 350 and the 260 over the coming months. For the legacy part, that is the regular Connex systems and also the Eden systems, I expect us to release within, I would say, the next 12 months. I think realistically we'll probably be looking to see this becoming available early 2017. It will not be released, however, on the desktop system. So the Object 24, the Object 30, at this moment in time, there is no plan to release the soluble solution for those platforms. But for the Eden and the Connex, within the next 12 months, hopefully sooner than later.
Okay, and can you use PolyJet for something like jigs and fixtures or tooling, or do you need FDM for something like that?
Okay, so I think, I mean, I've highlighted that there is obviously predominantly the PolyJet is suitable for the prototyping, and it's the performance materials in the FDM world that are most suited to the tools and fixtures world. However, there is a grey area definitely, and again, it's very specific to the customer needs and the demands and the geometry of the parts and so on. So there is an area of overlap for sure, and obviously with the higher performance PolyJet materials, the digital ABS in particular, I'm sure, or I know there are some customers who are finding that material is capable of being used in some form of tooling, some embossing applications, for example. The digital ABS material is very well suited. Obviously, the ability to produce a part with extremely smooth surfaces, that's a necessity, is a great advantage when produced in the PolyJet world because of its fine layers. And the need to process FDM parts if smooth surfaces is needed because of the thicker layers. And also with the ABS or with any PolyJet material, to be honest with you, the production of an inkjet mold is something that's very, very strongly on the increase in the world of PolyJet. Customers are using their inkjet systems, their PolyJet systems, to produce inkjet molds, not to compete with the aluminium or the steel molds, obviously. But if there's a need for a one-off or a short run, maybe that short run, depending on geometry, could be anything from a few to up to 100 parts, there is a capability to also use that material in that particular application. It depends on the geometry set. It's maybe not going to be an answer for every single need, but there's definitely a capability and lots of information available on our website if you'd like to explore that further. And of course, contact us with specific questions, and we'd be happy to share more details on that topic. So the answer is basically it's not as cut and dry as it's maybe appeared in my presentation. There's definitely a possibility to use PolyJet for tools and fixtures and jigs. But it's down to the geometry, the shape, and the individual needs, which our partners and specialists in the regions will be more than happy to help you learn more about.
Okay, thank you. A good question here. When will Stratasys have metal?
When will we have metal? A very, very good question. The question of will we have metal, it's a good question, because it's not will we ever, it's when are we going to have it, and I think that's the right question to ask. I think it's a matter of time. I hope it's a matter of time. Obviously, at this moment in time, we do not have any metal in our portfolio. Having said that, Stratasys, the organization, is the biggest single producer of metal parts. We have a service providing organization in the US called SPM, which is the single largest service provider with all types of 3D printing, including metal processes. So that's one part where we covered. Our own technology at this moment in time is not covered. We don't have it. We're a very focused on plastics company at this moment in time, and we see great opportunities thanks to the ability to print lighter parts and to lower costs compared to also metal parts, but still have the same performance. But it's I'm skipping around this, but I'm sure there is a desire and a will to have metal when the time is right. Okay, I know there's a lot of noise about metal at this moment in time. I know that it's a very interesting topic, and I agree it's something that should be thought about very, very seriously. But I'm unable to say at this moment in time when we would ever have metal in the portfolio. But I would be surprised if it wasn't a case of when and not if.
Well covered. Another question here. Will Stratasys open up its systems to third-party material suppliers?
Okay, open up our systems. That's an interesting one. Okay, so open and transparency is key here. I think we're probably aware that there are alternative suppliers of STM materials in particular out in the field, and this is something which is there. We try to protect our systems, I think is a fair statement, from any non-genuine materials. Not simply, but obviously it's a commercial issue. But I think the key point is that we go through a great length and invest a lot of money ensuring that material development are completely aligned with the product performance. Okay, we pride ourselves on producing production-grade systems, and the compatibility of the material with the settings on the system, with the system itself, is hopefully ensuring a high level of repeatability, of reliability as well. So I would say the key here is that we cannot prevent, but we strongly advise against the use of third-party materials. We do, of course, look to work together with third-party companies who can provide our install base with additional value, and I think that's something you'll see over the coming years to fruition. We've become a more open company, and we look to benefit from the knowledge and know-how of other companies so that we can provide more enhancements. But it's a very, very, it's a fine line of allowing our systems to use anything. I think the control, the ability to ensure the systems remain reliable, that we can ensure that they are production-capable systems with the reliability that you need. It's very challenging if any system can use any material. So for the time being, we try to encourage the use of the regular materials.
Okay, we've got time for just one more question now, so I'll go with this one. With so many different technologies out there, sometimes people can find it quite hard to choose the right printer. So how can anyone be sure they'll not be investing in the wrong system?
Okay, I think that's a very interesting topic given the world that we live in today. I'm sure everyone's aware there is a lot of noise in the industry today. I mean, we went back 2-3 years ago. There were basically 2 or 3 main suppliers to the industry. Today, there are, hundreds, if not thousands, particularly in the entry level. There is a lot of noise and confusion, possibly, on what's really what's value for money, I think, is probably the statement here. So, but there are some big players coming to the market as well. We know this, and it's clear that they have or claim to have very interesting offerings. The decision to invest in technology today should be based on what is best for your company today. I think there is great opportunities, continuing development of materials and systems, as hopefully you've just seen and heard in the webinar I've just presented to you. And we do everything we can to ensure customers who have invested in the technologies that we've developed over the past years benefit also from new developments on the material side, or even functionality of the systems where physically possible later on in the date. I mean, it's not always possible. Sometimes a development is so fundamentally different it may not be possible to upgrade the system. So obviously in those cases there's possibly a challenge. But having said that, Stratasys has always and will always offer its customers a very interesting trade-in option, both through and direct and obviously via our partner organization, to ensure that you can receive value from the investment made many years ago and upgrade to a more performance enhanced system that may be introduced at a later date. Okay, I think waiting is an issue. If you keep on waiting, you may never invest. I'm sure developments will continue for many years to come. Bottom line is, if you can identify an application, a process, a solution that will meet needs of your business today, will help you save money, will improve your overall production development plans, it's the right time to invest. Keeping waiting is possibly going to mean you're not competitive and you're missing opportunities now. So I think that's the statement I would put on that question.
Okay, thank you, John. I think we'll close the Q&A session there. If we didn't manage to fit your question in, don't worry, the team will pick up with you following the session. John, just want to ask, are there any final thoughts you'd like to add before we close?
Well, no, I think I just close on that. Thank you very much for your time, everyone, again. I'm just going to try and move this slide one more. Okay. Basically, we are here to support. We have a very competent and experienced organization in the UK. I presume we have a dedicated UK audience on the line at the moment. So there are lots of experts. We can take a lot more detail into your specific requirements. If you do have more questions, there is an email on the slide I'm sharing with you now, stratasys.en@stratasys.com, and we will make sure that someone gets back to you as quickly as possible. Alternatively, if you'd like to touch Stratasys a little bit closer and you'd like to come to one of our roadshow events that's happening in June, and you can see on the slide there will be a roadshow at Old Trafford in Manchester on the 8th of June, at St George's Park and Burton-upon-Trent on the 14th of June, and in Twickenham on the 23rd of June, where you will again find experts available. There'll be a system, a machine, and more informational materials which you'll be able to get closer to and answer your questions. Okay, so thanks for your time, thanks for listening. I hope we'll hear from you in the future with more questions, and who knows what else will come out of this session. Thank you.
Great, thank you very much, John. Just so you know, you will shortly receive an email from us with a short survey about today's session. Do take just a few minutes to fill this in. We do really appreciate your feedback. This webinar will also be available on demand over the next couple of days over at tctmagazine.com. You'll be sent a link to that in case you want to recap on anything you've heard in today's session. So what's left for me to say now is thank you to John Jones for your presentation, and also thank you to you for your attendance. We do hope you'll join us again soon for another TCT hosted webinar, and I hope you have a great rest of your day.